All right, so what came after this was that there were people who talked about, okay, how was the atom made? Because proton had been discovered, then electron has been discovered. I'm not sure if proton had been discovered, but electron definitely. Yeah, I think so. Yeah, positively charged particles had been discovered. And then in 1911, a physicist from New Zealand, Ernest Rutherford, working at the very other side of the world, England, UK. I think he was at Oxford. Yeah. Sorry, Cat wanted to go out, but like cats, he would just not go out when I opened the door. So, okay, so in 1911, Ernest Rutherford did a series of experiments, did an important experiment. Which helped establish the structure of the atom, okay? And what Rutherford did was that he found a source of alpha particle, probably a radioactive source, that emitted alpha particle. So alpha particles, now we know, consist of 2 protons and 2 neutrons, okay? So they're pretty heavy. And, then there's a collimator. And so you get a beam of alpha particles, a streamlined beam of alpha particles, and that is scattered off a very, very thin gold foil, okay? So gold foil. So the gold foil was so thin that it was not bigger than a few atoms wide. And then it was so thin that the alpha particles went through. And most of the alpha particles were barely deflected, okay? So most of the alpha particles were barely deflected. But some were deflected by a large angle and even backscattered. So from this, what Rutherford, and also he did a quantitative analysis. I'm just telling you the qualitative story here. And the quantitative analysis should be part of a classical mechanics course, as it was for me when I was undergraduate. So what Rutherford argued was that the atom consisted of a heavy, positively charged nucleus So gold is a pretty heavy atom. So that's why it was, whenever the alpha particles hit the gold nucleus, it got deflected or backscattered very easily. And it's surrounded by these very light electrons, which are going around the atom in some sort of orbit. Okay, so these are the electrons. Okay, depending on the gold will have lots of electrons, and doesn't have to be circular, can be elliptical. Okay, so this is the picture this is the Rutherford model. So because the electrons, the mass of the electron is about, if you take the mass of the proton, it's 2,000 times lighter. And therefore, if you compare the mass of the electron to the mass of the alpha particle is about 8,000 more heavy. And therefore, when it interacts with the electron, there's hardly any deflection. Okay? So this is the Rutherford model, but the Rutherford model has a very, very fatal flaw. Right? Can someone tell me what that flaw is?
The electrons would lose energy.
Exactly. So the Rutherford model is based on an inverse square law, right? Because we know from Newtonian gravitational physics that if two particles, the force between two objects is proportional to the inverse of their distance, then they give rise to if one of them is very heavy, then you can they form stable orbits, right? If this was the only law, right? So this is known as Kepler's law. What is Kepler's law? Kepler's law states that for an inverse square law force, say with a heavy object, say the sun, the smaller planets, they are going to orbit the sun in ellipses with the sun being placed in one of the foci. So these are the two focuses or foci of the foci, I think. Anyway, I'm not sure. Of the of the ellipse. So because the Coulomb law is also an inverse square law, but in that case, it's a much stronger force because, as you know, electromagnetism is about 10 to the power 40 times stronger, right? So in that case, it'll be the charge of the electron and so this is minus Q, and the charge of the nucleus, sorry, which is going to provide with the inverse square law. However, because electromagnetism is so much stronger than the Newton's law, the electromagnetic radiation that will be radiated by the electron would be of a much, would be a much greater amount than, say, the comparative, gravitational wave that we now know is going to be also emitted by two objects circling each other, like the sun and the Earth. So, according to classical physics, the electron's orbit would become smaller and smaller until it collapsed into the nucleus, and therefore, the Rutherford model failed to account for the stability of matter. Okay? So. Okay. All right. So this is where classical mechanics again failed very spectacularly. So then in a few years later comes Bohr, Niels Bohr, the very solved and sophisticated Danish physicist, and he made a huge contribution to quantum physics by his Bohr model, which is our next topic. But before we go to the Bohr model, do we have any questions?
I have a question.
Yeah.
It's more of kind of like a historical question, but the people didn't accept the atom at the time of like Boltzmann, and later on the atom was proved to actually exist. So my question is like, nowadays people dismiss things like string theory. Do you think that they shouldn't do that the same way that, because the atom was just kind of cast aside because people couldn't see it?
I mean, a lot of string theorists would say that that's a good argument for not rejecting string theory, because string theory, it may not be consistent, it may not be there is a good chance that it's a theory of quantum gravity. But because the energy is needed to experimentally verify string theories is going to be outside the scope of future experiments experiments that we can foresee in the near future, right? So from that point of view, string theory is definitely still has a chance to be a good candidate for quantum gravity. But one of the reasons why people dismiss string theory is something else. And the idea has to do with something called the landscape. And the idea of the landscape is that string theory intrinsically predicts that the space-time dimension is greater than 4. So string theory only works in higher dimensions. And that is something that we do not see in everyday life. Now, string theory has a very, very elegant way of solving this. They say that, well, the canonical string theories are 10-dimensional. So they're 10-dimensional. And what string theory says that 6 of those dimensions are curled up in small, very complicated looking manifolds. They are
Calabi-Yau manifold.
Yeah, they're Calabi-Yau manifolds, but they cannot be exactly Calabi-Yau manifolds. They have to be some kind of cousins of Calabi-Yau manifolds. The Calabi-Yau manifolds predict that the large four space-time dimensions be supersymmetric. We don't see that either. So string theory invokes all these very beautiful and elegant idea for its consistency, but it's far from us, establishing that. Now, the thing about a Calabi-Yau manifold is that there are many, many parameters that can be adjusted in the Calabi-Yau manifold. For example, each of these, these are called cycles. They can have different sizes. You can have, generalizations of electromagnetic fluxes, wrapping around these. So there's like a dizzying amount of geometry and mathematics that can be varied on these, on these manifolds. The result of that is the 4-dimensional physics, physics has a huge number of possibilities. And these are, most of them, at least to our knowledge right now, are consistent possibilities. So string theory predicts something like 10 to the power, I'm not exactly sure, 10 to the power 10 to the power 500, or some huge number of, or it may be that one of these, some huge number of possible universes, all of them consistent. And people who don't like string theory, who are detractors, they say that, well, a physical theory should be able to predict. And when you have so many different universes possible, as possible prediction of a theory, how do we know that, then this theory is not describing our universe? And they have a valid point. And that's basically their problem with string theory. So it has to do with the landscape. Now, there are some possible solutions to the landscape problem, and one of them is the anthropic principle. Although it's not a very elegant solution. So, and the anthropic principle has to do with so for example, we might say, suppose that someday we are able to travel to different, say, planets and in our own galaxies. And there are like, hundreds of thousands of these planets. And so we have been sending signals, SETI and blah, blah. So far, we haven't seen any signal coming from this planet which would, say, betray that they hold intelligent life, right? So, one way of this, so we might ask the question, why aren't there, say, sophisticated life in more planets? One of the answers would be that, well, it's for a planet to sort of sustain life as we know it, it has to satisfy a lot of conditions. For example, it cannot be too big, it cannot be too hot, it cannot be too cold. It basically has to be a Goldilocks planet, which is kind of Earth is. And that basically, in some sense, explains why Earth has life and other planets don't. So this is essentially the main idea behind the anthropic principle, is that our universe is the way it is and not differently, because if you change the parameters of the standard model even slightly, in most of these universes, galaxies would not even form, or they would form, or they would just, like, the stars would die too early or too late or something like that. I'm not a really astrophysicist, but there are arguments which say that. Sorry, can you see?
Yes, sir. We can see the screen.
Yeah. So for most of the string theory solutions, the universe would look extremely different. So one of the solution of the landscape is the anthropic principle, which says that, well, our universe is the way it is because otherwise we wouldn't be here to see it. Okay. It's not a very elegant solution in my view, but some people like it.
I see. So what I'm getting from your answer is that there's a difference between why people don't like string theory and why people didn't like atoms.
I guess I don't really know that well why people didn't like atoms, because I was born in a post-atomic world, and I was told about atom from a very early age. But you see that there are analogy between different historical periods, and those are very important. But at the same time, every historical period is unique. So what I'm trying to say is that the objections that people had to the atom back then were probably extremely well-founded. Now, I am a string theorist. I did my PhD on string theory. So it's, I do think it's very beautiful, it's elegant, but I am not 100% sure that it's a theory that predicts our universe. If it is not, then it's some form of mathematics, right? But it's definitely a very elegant solution to a lot of the problems, a lot of the mathematical problems that plague quantum gravity. Okay. All right, so does that satisfy you?
Yeah. Okay. Thank you for the answer.
Okay, no worries. So